All right, I've got a couple problems here that kind of look at the thermodynamics of kinetics, which sounds like an oxymoron, but more along the lines, it would be better to say the energetics of kinetics. I thought 933 was kind of a cute problem. This looks like something maybe our friends in the biology department would do. That is, measure the rate of crickets chirping. This sounds kind of high to me. It says at 27 degrees, the crickets were chirping at 200 per minute, but at 5 degrees, only 39.6 per minute. Even though this isn't really obviously a chemical rate, we still could consider the rate of the chirping proportional to some kind of mythical rate constant. What would be the activation energy of this kind of thought problem? And could we use our result to predict a rate at a different temperature? So what we want to do is get an equation that, remember we had the combination of two different Arrhenius equations at different temperatures to yield this, where we have a case 2 and case 1 defined, which just allows us to do a bunch of different things. We could find the activation energy of a reaction if we know some rate constants. We could predict a new rate constant if we change the temperature, or we could figure out what the temperature is if there's a certain rate we want to achieve. This one is all about finding this activation energy. Whoops, I did that again. If we're going to consider rate proportional to a rate constant, let me just rewrite this as the rate in trial 2 over the rate in trial 1, equivalent to our right-hand expression. And as long as you keep consistent which case you have, let's call the colder temperature case 1 and the warmer temperature case 2, and plug in our values. So I have natural log of 200 over 39.6, and I'm going to use the right-hand side to solve for EA. Always remember that we use the R that has joules in it if we're doing a problem that has energy in it. So my temperature 2 is going to be 27 plus, so I get 300 point, I guess I could say 0.15. And I'm going to subtract 1 over 278.15. Put that in my magic calculator, and I get an activation energy of a pretty big number. I get 51.1 kilojoules per mole of chirps, I guess. And then in order to use that piece of data to figure out the rate at a different temperature, I'm going to use my 15 degrees Celsius. I'll use that as my rate 2, what I'll go after, and turn this guy into joules to make all the units work out. 8.314. I'll be a little lazy and not write the units, but I'm going to put my 278.15 as, oh, that's actually a mistake. The 15 degrees belongs in the second slot. So I'm going to put 288.15 right there, and my 278.15 is there. So just to review again, here I kept case 1 as 5 degrees, and for the second part, case number 2 is going to be the 15 degrees. So this whole thing gets multiplied out to give me a rate at 15 degrees of 85.2 per minute. If we're going to consider another sort of thermo, again in quotes, consideration of a kinetics problem, talks about this electron exchange between a naphthalene and a naphthalene radical. You might expect if a naphthalene has this extra electron, it's going to be very, very reactive. And essentially that's what we're being told here, that this electron is just going to be kind of tossed around like a hot potato from one naphthalene to another about as often as the molecules come in contact. And that's what it means by diffusion controlled. If you have this solution, it doesn't have to be a solution basically, you could just maybe have an electrochemical cell filled with naphthalene in it. This electron is going to bounce around from one molecule to another just about as fast as you can get. And that's sort of indicated here when you look at these rate constants, which are awful fast. The expression you want to use here, I think, was 941 from your text. My text is a little bit out of reach, but let me use a little smaller font here. And I did have some notes here that the rate constant, when kind of blown out to all its thermodynamic glory, looks like this. It's got multiple pieces. There's this exponential term that contains Boltzmann constant and temperature and Planck's constant. There's an entropy term, and we've got an enthalpy term. Just to remind you that this double crosshatch, that refers to the state being the transition state. So when we're talking about a reactant going up to some transition state up here, it's almost as if we're treating the transition state as a final state. It's not really, but we're still applying the same terminology to the final minus the initial kind of idea. So this equation can be turned into something to do a plot by using our old friend applying the natural log to each side. So you could have the natural log of the rate constant over temperature. That ends up being your y axis. It's going to be equal to natural log of the Boltzmann constant over Planck's constant. And then two more terms. We've got the entropy term over R and minus the enthalpy term over RT. And I'll use these boxes to indicate what actually the plot you should do is. So you really want to plot the natural log of the rate constant over temperature versus 1 over t, and then work out what your intercept and your slope is going to be. The slope is just simply the delta H piece. Really, I should say minus delta H over R. Let me switch colors here just so you can see this clearly. So the slope is the minus delta H over R, and the y-intercept is going to be everything else that's left over. And so I have natural log of Boltzmann over Planck plus delta S over R. The best fit line for this plot I did, and I got minus 1302 x plus my y-intercept had a value of 20.24, and therefore if everything was put in the calculator correctly, you get 1.08 times 10 to the 4th joules per mole, and the delta S term ends up being minus 29.3 joules per k dot mole. Not exactly sure why this is getting more ordered, but that's the number that popped out. Not a very, very large value for delta S. I think I'd have to do some background on that to find out why that's negative. But we have an expression for EA. And that's going to be 1.34 times 10 to the 4th joules per mole. finally, the delta G term is going to be the combination of the two terms we've already calculated, the delta H term minus T, the delta S term. And if we plug in the information we already had, get 1.98 times 10 to the fourth joules per mole. So that's a lot of calculations there, but these are the values that you could get from studying the, quote, thermodynamics of kinetics.